Thank you, everyone, for joining us today. I'm the moderator here today, Dak Bush, VP Systems Engineering here at Cumulo. We're here today to talk about Cloud Data Fabric, how you get any of your data at any location with total control. With us today are our speakers, our CEO, Douglas Gourlay, Brandon Whitelaw, VP of Cloud, and Aaron Passy, our Chief Architect. So this is super exciting technology. It is truly transformative, and I will shut up now and hand it over to Doug, who's going to introduce you to Cloud Data Fabric.
Awesome. Thank you. And let's go to the next slide too. Boom. That is like one of the worst pictures of me. We do not need to be seeing that one for long on the screen. Awesome. Thank you. Real short and kind of simple to the point. In 2012, Cumulo, we set out to build the world's most advanced file system and never look back, right? From the data center to the cloud, saying, let's be unbound by the legacy limitations. We envisioned a future where everything could be available everywhere instantaneously. And let's let our clients do like magical and amazing things, from bringing together artists and storytellers from around the globe to work on a feature film, or sharing cutting edge AI enhanced medical research with top physicians, to harvesting fleets of data, like terabytes per car in ADAS clusters and modeling it to make the roads safer. Sure, we could have worked on an LLM that helped put, I don't know, Chegg out of business and helped me cheat on a college test. But the things that save people's lives, materially impact humanity, those are the ones where we've been spending our time and energy working with our clients to do just incredible programs and projects. This announcement's about us extending that even further, taking this concept of a file system from being bound to a cluster to being unbound around the world. So let's flip to that next slide. And what are the core elements of this? Well, a global file system that abstracts data from disk, treating all data across clouds and data centers as large elastic pools of data in the data core, enabling hierarchical storage management, tiering, replication without affecting or impacting user access, or even having to be aware of the data's location. By abstracting the file system representation from physical data location, our Cloud Data Fabric frees application and data to scale and move independently. Second, a coherent edge cache, coherency being the key here. I had to deal with caching 20 years ago, and it was like, is my cache stale? Is my cache up to date? Do I have to refresh everything? Do I have to poll? A coherent cache allows for instantaneous data access without compromising the controls that have been necessary in the data world, preserving strict consistency, access controls, logging, locking, durability, without compromising performance, and vice versa, enabling performance without compromising consistency, access controls, logging, or locking. And real-time data collaboration with total control. When you combine these two, that large data core, multi-cluster, multi-cloud working together, extending the reach of the data with a coherent edge cache, then we can take large files, complex workloads, and allow follow the sun editorial suites, allow data to be streamed into the public cloud and prosecuted with a high-performance AI-enabled accelerated computing system. We can express data where we need it for maximum business value and let multiple engineers, artists, storytellers, designers, intelligence analysts work together on the data set that matters to them without stepping on each other, with block level locking and a globally consistent architecture. Next slide. Now, I'm going to bore you for a moment, but we have to do a shameless movie callback. History of the Data World, Part 2. Now, if you remember the movie, I'm dating myself. It was fun, though. Dude, it's a good film. Come on. So you get it. I'm going to take 30 seconds here. CPUs used to mount disks. Awesome. We wanted durability. Add RAID. Multiple disks. One fails. Life continues. Next evolution. Bottom 3. Controller-based NAS. Put a CPU in front of that. Now I'm using protocols. I'm using SMB, NFS, whatever, to access the data across a LAN, and the controller deals with it. Then the invention of scale-out NAS started a while ago. Keep adding nodes. data keeps expanding across them. They all represent themselves into the network, and I'm directly accessing it again using the same sets of protocols, SMB, NFS. Awesome. These architectures worked. They were great in the 90s, early 2000s. Way to go. Next slide. What were the inherent awesome things about them? SMB and NFS are amazingly good protocols, especially when going over a local area network. High performance, low loss. We found that large buffers helped attenuate speed mismatches or concentration as SMB, NFS are going to a smaller number of targets, and sort of a scale-in problem. And in that world, it's like, hey, throw some more buffers at it, performance increases, increased network capacity. It's great. Next slide. Fit to purpose for the LAN, sucks on the WAN. These protocols were not designed to go around the world. And when you're dealing with 300 millisecond round trip response time, very challenging bandwidth delay product, take a look at the Mattis algorithm if you want to have a lot of fun. Old school TCP cubic retransmission, not exactly exciting performance for the clients. But you maintain consistency. You maintain control of your data, you maintain locking, logging, all the things to keep all the InfoSec people happy. All of us as data practitioners, we need the controls, but in extending the distance, we sacrifice performance. Now, the historical solution was, boom, next slide. History of the data world, part 2 continued. You'd replicate. Now I'm doubling the amount of storage that I have to have in order to ship it around the world. Try to maintain consistency and coherency there, but allowing an improvement in performance. If these are across autonomous systems, or these are using non-coherent caching architectures, you are sacrificing consistency, locking, audit, data provenance, security on the altar of performance. So it unfortunately were these two Venn diagrams, well, these two circles that weren't a Venn diagram. There was no middle. There was no ability to say, how do I get the best of both worlds? Can I get performance and consistency and correctness and durability and audit and logging and locking and provenance? Can I preserve all of these attributes without compromising performance in a multi-protocol world when I'm dealing with users and machines all at the same time? Fundamental problem. This is what we've been focused on solving. Next slide, please. First step in solving it is, how do we take not just a data set, not just a cluster, not just a cluster of clusters or two clusters in a data center. We take multiple data centers and multiple public clouds, wrap our arms around this. This is a global data core. This is one large elastic pool of data. Then as a good friend of mine used to say, every problem in computer science can be solved with yet another level of abstraction or indirection by wrapping our arms around all this data, whether this is, by the way, an all-flash cluster on one part, a cheap and deep on another, a secure enclave for PCI DSS data, HIPAA records, GDPR data, if it's things that have specific provenance requirements, or it is, again, multiple clouds and multiple classes of service, being able to have access to lots of data stores and being able to put data where you need without changing the expression or representation of that data to the client, whether they be a machine or a user. The freedom to put the data where it best supports the business operationally or from an engineering perspective as a storage professional, without necessarily having to change pointers or things on the application side in order to have this freedom and make these changes and choices. Next build, slide, whatever. So users connect in through the global data core. That global data core can then express itself over the wide area network around the world to a coherent edge. Whether users connect in through a cache coherent edge at a distributed site or are local and connecting in through the same cloud data fabric, the user experience doesn't change. The data movement can happen in the back end. Replication can occur, hierarchical storage management, data tiering, or as one of our customers said, and I'll paraphrase slightly, most of our file and object stores are the junk drawers of data. Our goal is to be the Marie Kondo of that data, to allow it to be sorted and organized effortlessly without having to change the workflow, without having to change the application, allowing for 3 core capabilities: the global data core and a global file system that abstracts data from disk, being able to then build these high performance cache or coherent caches at the edge that allow us to extend the reach of that data to where you need it and express it there almost instantaneously. And then to apply those, as Aaron will talk about and Brandon will talk about, to looking at workflows in worlds like media and entertainment, intelligence and analytics, CAD/CAM workflows, semiconductor design, where I may have a large group of personnel distributed around the world that need to work on a set of data. The data is maintained consistently without blocking each other or locking each other out from working on it. And frankly, in a world where the artists oftentimes have the tools of their choice that they want to use. So, Aaron, can you walk us through a little bit more of the technology, how this works? And I'm going to add one thing. Aaron's job title is not just chief architect. Aaron is also one of the founders of this company and one of the brightest minds I've met in the world of file systems and architecture. So I have an interesting ask of the audience as we go through Aaron's section. Help me abuse him, okay? He just had a birthday. For his birthday present, ask him the hardest questions you possibly can. And Steve and Dak are probably accruing swag that we're going to send out to the people who ask the most fun, difficult, and engaging questions of Aaron. And also to everyone who didn't ask me one of those, thank you as well. I greatly appreciate it. Aaron, on to you. Let's make this fun.
Yeah, just keep your questions coming in the chat, folks. Thank you.
And Dak, interrupt us if there's a great one, okay?
Absolutely.
Awesome.
Hey there.
Go for it, Aaron.
Well, with that intro, I am ready to get going. Um, so far, this presentation has been a little bit abstract. Let's make it a lot more concrete and sort of dive in to what's going on. Next slide. I want to zoom way into, let's say, one of the fibers of the Cumulo Cloud Data Fabric. If you look at the picture on the right, it is a single portal. It's representing a single portal, what we call it in our system. The box on the top is the edge that Douglas talked about, and the box on the bottom is some cluster somewhere in your data core. So actually, either of these can be any sort of Cumulo cluster. It can be a 1-node edge cluster. It could be a 100-node cluster with a terabyte per second throughput. For either the branch or the core. The connection between those two is what we call a portal. So that at its core, okay, that's a bad word. The branch or the edge is a cache, and it's a write-back cache. And that is how we get this local performance for remote data. Any data written in there will get written to the cache, and then we will actually acknowledge the response to the client immediately. Reads will fetch on demand the data that it needs. Both data and metadata are fetched on demand, and this is really important for, let's say you have 10 billion files in your file system. Well, you can't wait until all of those are cached before you allow access. So you can spin up one of these edge caches within seconds, and then all your data is available immediately. The data is transferred at block level granularity. So if you have a 10 terabyte file and you need to read 4K of it, we'll only wait for 4K to get across the link before it'll actually return it to the user. We don't have to download an entire file to be able to see any data in it. I already talked about instant setup. And the amount of data transferred, we have a minimal amount of data transferred. Again, if you have this 10 terabyte file and you append 2 blocks to it, the amount of data we'll send back is 8K to do that right. We don't have to transfer full files in either direction. So all of this ends up making local performance for remote data. So that branch can be in Tokyo while the core is in LA. That works just fine. And you can get this really great performance. Let's go to the next slide.
Hey, Aaron, we got a question from a large M&E company here. They're curious, what protocol do we use between the systems to copy and move this data?
Yeah, the protocol between the systems is our own proprietary protocol. I'm going to go into it a little bit in the next slide. We have methods for this protocol for cache fills, and we have methods for pushing logs back and forth, and we also have locking and stuff to be able to make all this work, which we'll talk about in a second. Can you go to the next slide? Yeah. So having high performance cache is kind of useless if it's not correct, if it's not consistent. And so the biggest part of our design and the sort of most core piece of our architecture is how do we make it consistent? How do we get, in fact, 100% strict consistency? And well, first of all, what does it actually mean to be strictly consistent? So if you imagine having a client and you mount the edge box and you write a file and you have that same client mounting the core box and you immediately read that file, we guarantee you get the new data every time. Not only that, we guarantee you get the new data in the face of failures, in the face of network partitions, in the face of different things rebooting, of your client rebooting, like all these things. You will get the correct, consistent data as though you were attached to wherever the data lives on your client. So to reiterate, this cache is indistinguishable from data read on an edge cache is indistinguishable from data read on the core. It'll have the same metadata, it'll have the same permissions, it'll have the same data, of course. It'll have the same file ID. It looks as though it is exactly the same data. The way that we actually achieve this is through a combination of logical logging and intelligent locking. So I want to talk about this. We basically, every write that goes into either side of this link, you write into the data core, it'll actually make a logical log of whatever it is you write. And so those are things that it's now dirty on the core that that needs to get sent over to the edge. And the same thing on the edge. If you write something on the edge, it'll put it in a log, which is the set of things that need to get sent across this portal link to the other side. And the locking is we have global locking across the entire system here, across both the core and the edge, which will allow you to which ensures consistency. So basically, when any particular file is accessed, if it needs to acquire the lock, we have a system underneath the covers that forces the log to be replayed for that file before it's allowed to get the lock. So therefore, you always get the newest data before you have access to it. The locks are all cached. So once you get the lock the first time, it stays cached and it's actually super fast. It's a local memory operation to get it the second time. And that ends up allowing this consistency that we have built in from the beginning. A really key point here is that you can't achieve this consistency. You can't achieve these semantics with a bolt-on system. You cannot put something on the side that transfers data back and forth between systems and have it consistent without it participating in the locking protocol of the file system itself. Our logs themselves are written transactionally with the data that's written. So you cannot get a log entry without having written the data, and you can't write the data without having a log entry. They're atomic in our system, which is something that's really critical for correctness. So this system was built with the core file system. It actually natively understands geographically distributed systems. So with the headline being we have remote data, but we have local semantics.
Hey, Aaron, along those lines, a ton of questions rolling in here. So I'm just going to hit you with a few here for the audience. How much of the file system metadata is cached at the edge, and how are large metadata scan operations optimized?
Well, the metadata is fetched on demand, just like the data. So when you do an ls on a directory, if the dirents for the directory are not yet cached, it'll do a cache fill operation, bring the data over, and then it'll become cached. So we cache as much as that you've actually looked at. I guess one other thing I didn't mention before, which is interesting, is we have prefetchers across this. So we actually look at the particular access pattern that's going on, and we'll prefetch stuff ahead of time to be able to make the latency, the apparent latency at the cache much lower. And so this actually is for files. Obviously, if you're reading a file, it'll prefetch ahead in the file so that your next read will become low latency. We do the same thing with metadata. So if you're reading a directory, we will prefetch the metadata ahead of time and bring it into cache. For the question of full data scans, if you do a full data scan from one of these edge, at the end of the scan, the entirety of your metadata will be cached on the edge. Is sort of how that works. And so then if you do that scan again, it'll all be a completely local operation to go and scan the data again on the cache.
Thank you, Aaron. Super thorough. So a couple higher level ones here that I think are good for the audience as a whole. Is an edge system then required for all users, or can users mount the local cluster?
Yes. So on this diagram, we've labeled edge and data core as separate systems. So the edge here could be a little 1-node cluster. It could be a 100-node cluster if you need a lot of performance. So if you have a burst render workload, you can actually have an edge that's much bigger and much higher performance than the core, so that and you can have hundreds of thousands of clients all reading data off the edge. But you don't have to. You can actually have some of your clients can be directly attached to the data core. Some can be directly attached to the edge. In fact, if your data core is in your headquarters and the people who are in your headquarters can just attach directly to it, and you have a branch office, 3 cities away, they can go and you can put an edge device out there and they can attach to that. So everybody gets the low latency and everybody can get the consistent access to the data.
Yeah, any data anywhere, right? So one more question here that I think is pretty salient given the mission of Cloud Data Fabric. It's a good question. How does this differ from what the industry knows as GNS? Is this the next evolution or a new product?
Well, that ends up being a question of marketing terms in a lot of ways, but oftentimes GNS actually refers to stitching together a namespace, and it doesn't talk about the semantics and the caching and the performance of it. So a GNS system let's say the legacy GNS system, oftentimes is like DFS or something. It will actually allow you to see multiple namespaces and see remote systems, but you get none of the benefits. You get none of the consistency or the performance of a system like we built. And so we're calling it something new because it is new. Like this actual consistent cache is a very new thing.
Excellent. Thank you, Aaron. I think I'll pause for questions now and let you go to your next slide.
The next slide's a small one, but yes.
Yeah, keep the questions coming. It's so much more fun.
Absolutely. So these portals that I talked about before, where we zoomed in onto a single one, they're really important. They're actually per directory. So you can actually have your home directory go to one, be expressed at at some branch office. You can have a research directory at a campus office. You can have the same directory go to multiple edges. So in this particular case, in this picture, the research has a campus edge attached to it, and a cloud edge attached to it. And it has the same consistency as before. If you go and write data into the campus edge in this picture, and then read it from the cloud edge, you're guaranteed to get the new data. If you write, or if you read it from the data core or whatever, these things become peers in this system, and reads and writes and all are completely consistent across the whole fabric.
Okay, some more questions here for you, Aaron. Um, uh, sorry. How do you deal with variable delay due to distance? An example that they used was, will local data sources flood the core versus longer distance, higher latency sites?
The actual data flow is asynchronous. So if you're writing into an edge, it writes persistently on that edge, and it writes into the log that's on that edge. And in the background, we have a log replay engine that actually pushes those log entries back to the core in that example. And so this actually allows you to decouple the performance of your WAN compared to the performance that you actually want to write into the edge. So you can write faster into the edge than your WAN bandwidth. The question then becomes in the core, you want to go read that. What we'll do is we'll actually block the read until the data gets there. And of course, we'll actually have that as a high priority. Like if something is waiting on a particular piece of data, we will push that first. But in that way, like it decouples the performance of access to the core and the edge, and we maximize the use of the link in the middle as much as we can, so that we get the best performance as possible with the setup that you have. Did that make sense? Yeah.
Makes sense. Makes sense to me, Aaron, but I've spent a lot of time thinking about this, and I think it's, a lot of people seeing this for the first time, so hence a lot of questions coming at us.
Absolutely. Hey,
What?
Dak, one thing I'll add on that is we're just moving there's a level of protocol optimizations that are happening between the edge and the core in a way that a lot of the things that traditionally would have had to go all the way across the WAN are processed locally at the edge. But we're moving the smallest amount of data when it's requested. So, moving just the blocks that are needed with then an aggressive and preemptive read ahead cache allows for that to happen in a way that becomes very seamless to the customer. And one demo, I think it's you who showed this to me, Dak, was remember the demo you guys did where you opened up the file and the cache started filling, and it started filling like immediately on the video, of course, but also started filling in at like minute 46.
Mhm.
And we're like, why is it filling in at minute 46? Well, it turned out that's where the editors were working on.
Mhm.
So it started automatically filling at the locations that were most utilized by the users of the data. So then when they would go to that portion of the file where they were doing their VFX work, it was, again, almost instantaneous.
Yeah. Yeah, the predictive caching coupled with, is a key part of Cloud Data Fabric. And a simple way to think about it is based on the bandwidth you have, it'll use all that it can get its hands on to give you a visual image. Would be like a wave of data behind the offset that you've chosen to read at in the file. So while you're drinking from your 1, 2, 3 gigabyte per second, or in networking terms, 10, 40 gigabit per second client connection, we'll use all the bandwidth we can to get your data into the cache as quickly as possible. But all the while, only moving the data that we really need to put in that cache so that we make efficient use of your WAN bandwidth. Another one here I think is key, Aaron. What do these services run on? Do they run on conventional servers, or do you need GPUs, FPGAs, etc.?
Yeah, so all of our software runs on industry standard hardware or cloud instances, or basically anything. Um, the only thing that we require for a system is you have some amount of SSD in it, and you have some amount of networking on it, and that is actually sufficient to be able to run the Cumulo software. And that works in the cloud, it works on-prem, it works in the closet, like for an edge cache.
So here's one. And I think this will be the last one before we hand over to Brian. Um, a question on how do you protect against fragmentation when file data is scattered across different parts of the disk, resulting in reduced performance? And I assume that they're asking that question in context of Cloud Data Fabric, um, whether it's local or remote.
I mean, it's more of a local question. For each, I mean, the local cluster itself manages its own allocation for blocks, and the answer to that is actually different on our erasure coded products, our on-prem products, and our cloud products. But for the most part, we have a lot of really sort of advanced allocation system that actually chooses good spots for the data to be able to reduce fragmentation. In the cloud, we rely a lot on temporal locality, which means that data that's written at near the similar time will end up in a similar place in the object store, and that ends up having a really big win from a performance point of view that way.
Yeah. Thanks, Aaron. And I mean, Cloud Data Fabric is abstracted from the things that are managing all that data on disk or wherever the persistent storage is, part of our really well architected, abstracted software architecture. Okay, so I think we'll pause on the questions for now. I'm going to hand it over to Brandon to take you through some use cases and examples. Brandon?
Yeah, keep the questions coming, everybody. We'll try. I think now, especially that I'm talking, Aaron and Dak can probably type some questions, and we'll circle back and go as long as everybody wants in answering them. But I thought it'd be helpful to maybe talk through some customer engagements we've had over the last, 12 to 18 months now of real world use of how we collaborated to help customers solve really what they thought were tomorrow's problems, but now realize today with this technology. And I couldn't love it more. I mean, I've gone on a lot of years, let's just put it that way, of talking to customers about wanting and needing this type of capability. And because the technology didn't exist, architecting halfway piecemeal solutions to try to address that, cloud adjacent things and, virtualized things, but not really to the promise of that, still had hardware requirements, and then replicating data everywhere to try to counter the access problem or the collaboration problem. And then, not only you, as Doug mentioned, paying for data twice, but now you have no single source of truth and trying to get that together and creating, just duplicates everywhere. And you think any one storage system is expensive. Wait until you pay for data to be in multiple storage systems, the same data, just because you want to provide access to collaborate on projects. It gets really, really challenging. So if we go to the next slide, I'll walk you through 3 top scenarios that I thought were the most interesting, just 3 of many. The first one really had to do with protein research. This is a hugely interesting space in medicine and development for new treatments for a wide variety of things. Actually, a pretty interesting case for AI interacting with this as well. But this customer had a scenario where they said, look, I need to be in the cloud for the on-demand burstable compute. I need to be in the cloud for being able to collaborate with other research groups. But at the end of the day, my instruments, my devices that are creating tremendous amount of data, Illumina next-gen sequencers, et cetera, they have to be physically on premises. They have to be, we're talking about putting, biological materials in these devices and producing, tens of terabytes of data per day. And today what they do is they kind of land it, stage it, and then copy it, or that's what they did. They kind of stage and copy data. There's a lot of copying. There was no real insights or connectivity between those sites. It was just pools of on-prem locations and then that cloud pipeline. And what we're able to work with them to design is this really global cloud data fabric where, you could have a small edge Cumulo system, all NVMe right next to the sequencers, grabbing that data. That data was written through that edge device. It wasn't landed and replicated. It was written through that edge device into a cloud pipeline where they did triage down on that data and all the other things to start working it through their pipeline with Nextflow, et cetera. And then at the same time, for downstream tertiary analysis, they had other sites where they had cryo-EM devices themselves, also producing a ton of data. Wanted that to be able to come in and cross-correlate. These things were disparate previously, creating a lot of copies, a lot of manual work, a lot of like kind of, I would say duct tape and paperclip of data curation and movement around. And today, now they have just one single data fabric that manages end-to-end data curation and access, where they can get, with our cloud native Cumulo system in the cloud, they can get burstable compute as different runs come in to meet whatever deadlines or projects, and ultimately just reduce the time to discovery. So this really has cleaned up the entire pipeline. And this is a situation, by the way, I saw countless times in my previous companies with, again, a lot of attempts to go from file to object. Well, I have to put it in S3 because if I don't, then it's not cost effective. And that's how I collaborate. But now that's gone. You can have a single system that gives you all the performance and cost effectively performant in the cloud, and then be able to connect those edge devices into it so that it's just one seamless architecture and pipeline. And it just provides tremendous benefit in being able to propel the science forward and accelerate things, even as now they're experimenting with new AI pipelines running into this at the same time. That wouldn't be possible if the data was trapped at the edges or they had to pay for it to be copied multiple times. Really, really effective. Let's go to the next one. So now going from super high performance, collaborative down now into PACS medical imaging. If we could progress, thank you. So this was a customer that said, look, we have to hold this PACS medical imaging data for a really long time. Expense is really important to us, but also durability and accessibility is extremely important. What we're able to put together for them, we had some challenges, by the way, initially. Challenges were, by the way, legacy applications. I don't know if you know, but a lot of the PACS applications, really haven't changed how they interact with data in 20 to 30 years. And so they're not really cloud compatible, even if they wanted to be. And on top of it, they have a lot of restrictions in them. For example, this one in particular had a restriction where it could only address two storage systems, a tier 2 cache and the long-term archive. And so what they really wanted was the ability for this data to live in Azure, in this case, because they wanted to be able to access Azure's OpenAI healthcare pipeline to do real-time tumor detection, AI detection, et cetera, on this data in a secure, governed way. But they still needed the pipeline they have built out on-prem with the PACS viewers and the radiology and everything to still work and not be disruptive. So kind of have my cake and eat it too. I want all the benefits of cloud, from higher durability, higher accessibility, lower costs, actually, as well as the accessibility to these fantastic new, services, AI services that Azure provides. But it's got to be seamless into my legacy application structure on-prem. And so the way this was achieved was a hot tier 2 cache on-prem that seamlessly exposed 20 petabytes of historical PACS data as if it was on-prem and local, at 12 nines of durability, even higher than a dual system on-prem, triple site accessibility. So in any scenario, they knew the data wasn't going to be lost and they could access it.
Brandon, I'm going to cut you off. Not because honestly, because I just wanted you to breathe. Okay. Just a second. But when you're talking this level of data durability, how does that compare in this multi-AZ environment? Like you said, to your classic dual controller architecture, but how does that compare to, say, a distributed metro cluster environment?
Oh, it's actually, so here's a really interesting stat. So today,
is that a softball, by the way?
No, but it's really interesting. So look, legacy scale-out file systems could never achieve like a stretch metro cluster like capability, because this requires like a dual acknowledgement right on both sites. And that doesn't work well when you have a true distributed scale-out architecture. It's always asynchronous. And everyone kind of just tolerated this, right? But now this customer actually found that, they went from a dual site replicated system that was providing about 9 nines of durability and managing that, right, in between those, most graciously 9 nines, to a 12 9 durable triple site system in the cloud, where actually you have 3 site resiliency. So instead of going from 2 with Metro, you go to 3 sites. Instead of like 9 or 10 nines, you go to 12 nines, and they don't have to do anything to achieve that. They don't have to manage multiple data centers. They don't have to maintain the DNS linking and the networking to make sure that it doesn't go down when they need it. It's all automatic. And so they can even fail over from one hospital to their secondary hospital in the case of a natural disaster and still have full, complete access to all that data and not have any management burden related to it. It's really fantastic. It's, I think, technically the highest durability available, durability and highest availability file system architecture ever created. Hands down. I don't think there's anything that even comes close.
Can you say that one more time? Just that last sentence. Just for posterity in the transcript. Just say that one.
Pure from the numbers. There is no other file system architecture that provides higher durability and availability than the cloud native architecture in a multi-AZ deployment without having to pay to replicate the data multiple times, like on almost every other architecture. Right. So tremendous cost savings. In fact, again, their cloud-based system was up to 35% less expensive than they were paying on premises. So they cut cost, they increased accessibility to AI data services, increased durability and availability, and never had to change a single thing to their entire architecture on-prem and their legacy application compatibility to get to the data. It's really amazing.
You could just say it's pretty badass, really.
Yeah. Yeah. I mean, all around, it was so fantastic to work on this project with them. Next one. And I would say that the group that's probably the most exciting about Cloud Data Fabric is our media customers who have been dying for the ability to facilitate global collaboration for years and really creatively trying to come up with ways to make it work. But especially post-COVID, the world is forever distributed and more teams, even some of the smallest studios that we interact with, go, oh yeah, I got a team in London, I got a team in Mumbai, I got a team in LA or Toronto or Vancouver. They're all over. They really need the ability to get this global workforce to be able to collaborate in a seamless way and at the utmost of artist performance and experience. You can't ever sacrifice that artist experience. And so this customer in particular had a workflow where they, were using PC over IP into a cloud region. It allowed them to be able to get tremendous performance and accessibility. Really, there's really no other option for high performance SMB access in really extremely high resolution, high parallel frame playout than cloud native Cumulo. And so to be able to burst on demand to not only meet the artist workloads, the utmost of most extreme artist workloads and Flame workloads and Premiere workloads, but then to be able to burst render, to be able to have that an edge system stand up separate than what the artists are using, so it doesn't affect their experience, and burst render to hundreds of gigabytes, if not a terabyte per second of throughput, faster than ever thought possible before. And then the last thing, by the way,
Brandon, wait, I'm just going to cut you off again, so I can't help myself. Could I burst render into, say, 3 different clouds or 3 different cloud regions and utilize the distributed capacity of multiple cloud providers and concurrently off of the exact same file sitting in my data core?
All your data everywhere instantly. So absolutely. I worked with customers at AWS who were extremely challenged by the availability of certain compute when it was crunch time to go render, and they had to go full throttle. Not only could you connect multiple regions like this customer did, both for their artists and their compute, you could connect multiple clouds. And so really it's just like bidding war, like who's got the best availability and price for the particular nodes that I want, and I'll be able to connect that compute to the data regardless of what cloud it's in. And being able to have that throttle to unlimited, they've gone plaid, is hugely valuable to accelerate these workloads and ultimately create this limitless bound architecture to get the work done, to build the experiences people love to consume.
Now,
I'm gonna pile on there.
Dak, hold on, shameless question, because you're probably gonna say the same thing I'm gonna ask you, but it just sounds so much better if I ask you than you say it. No offense. Not because if you just say it, sounds like you're bragging. Do you have a customer who is doing something like this where they're literally a data set is in one cloud provider and they're using GNS to get it to another in the media space without saying who it is?
100%. One of the largest US broadcasters has data.
I was asking Dak, Brandon. You're the silver.
Oh, sorry.
I wanted Dak to answer it.
Yeah, sorry. He does know about this one too. Yeah.
He's the one who told me about it.
Oh, okay. Sorry.
So that is absolutely going on. But I just wanted to say on the render workload, I wanted to pile on there. I think the biggest challenge for most folks that need to do burst render in the cloud is there's really only kind of 2 render pipelines. Every one of them is unique, but at the end of the day, they bifurcate into either know what data I need for this render job, or I really don't know and I got a big data set. And that's where Cloud Data Fabric can make your life so, so much easier. You just point it at your big pool of data on-prem and let your render farm go to town, and it'll just pull what it needs, cache it locally. Lots of rereads due to overlaps within the render jobs and textures and such. So pretty excited about freeing that workload in that hybrid cloud fashion.
But back to my question.
Oh, as far as multi-cloud for M&E workloads, or for that matter, any workload, absolutely. I think it's one of the questions that came in. It's named Cloud Data Fabric. Do I have to have this in? Does cloud have to be in the mix? No, we named it Cloud Data Fabric because you can use it in your private cloud, you can use it in the public cloud. Anywhere you deploy Cumulo, you can use Cloud Data Fabric. So on-prem, hyperscalers, private cloud, whatever your terminology for your infrastructure is, wherever you deploy Cumulo, you can leverage Cloud Data Fabric. So yes, hyperscalers and between hyperscalers for multi cloud connectivity, either natively between clouds or in a hybrid fashion with multiple cloud providers, as we were giving an example in a burst render scenario where maybe you can't get enough cores in one cloud. I could go on and on and on, Doug.
I know. I just want to give you a chance because it's kind of fun. Brandon, back to you, brother. Take it home.
So anyways, I think the thing that's really interesting about this was the new workload possibilities it opened up. Previously, they were kind of putting projects based on particular teams, and now they can align projects globally based on the particular talent of the mixed teams. They're no longer bounded geographically. And it's amazing what you see happen and how they change their pipelines now that this is a possibility. It kind of reminds me back in the day about learning back in the day, so to speak, of when, high-end amperage electrical came to factories instead of steam powered. And originally people just replaced all the steam machines with electric machines, and all the promise of revolutionizing didn't really change because they were still bounded to the constraints that led to the original architecture of steam, all the machines being right next to each other, bottlenecked for access. And it wasn't until people started completely rethinking the art of the possible, of how they optimize for the best outcomes, that they started seeing the real true benefits of it. And so, this can have an immediate impact to customers right day one with where it's at with the technology. But even further, I love being able to collaborate with them on that possibility of like, wow, I never really thought about that. Now I can do this, or now we could do this, and completely changing how they see resources, people, and access to data in a whole new light.
That is awesome. Okay. So let me recap a little.
Yeah.
Let me recap a little bit here real quick. The workflows and workloads that we generally support across our 1,000+ customer base are myriad. They're legion. We have customers that have told me we're building their grandchildren's favorite character on Cumulo, and our job is to keep it and preserve it durably long enough so her grandchild can watch it in its unfettered form. We have customers who say because of proteomics and genomic modeling, the cure for cancer is stored on Cumulo. Now we need to find it. We need to make it available and accessible fast enough to the accelerated computing AI platforms and models that cure gets delivered quicker. We have customers who are making 3D simulations of human brains, tracking the sources of ALS and Alzheimer's and Parkinson's. We have another customer who models wildfires and where they're going, get that information into firefighters' hands and know where to build a fire break or where to evac. We have customers in national intelligence and defense doing their mission. We have customers figuring out the best ways to generate energy, the safest, cleanest, most efficient ways to do it. And we have customers who build autonomous driving systems that every time you're distracted for a second with a text message, the car can stop automatically. The future we're talking about in this world, everything we're looking at is literally as an industry or humanity, whether you're talking AI or ML or this expanded definition of AI that was everything we used to call HPC, all of it is data-driven. That data is all unstructured file and object data. That data is scattered. That data is in data centers, it's in campuses, it's in clouds, it's in research partners. I was talking to the CTO of a research institute who said, we have 350 petabytes of data. It's in 2 data centers. It's in Amazon, Azure, and Google. It's in our 7 research campuses. It's extended to our 25 research affiliates and partners who need access to it, and they're global. And then we need to get all of it to an AI processing facility we have in another state. And if that runs out of capacity or we're spinning up something new, we need to use it in the cloud too. We need all of it. We need everything. We do need it everywhere. We need it instantaneously. And we can't lose control of it because the data is critical. So yeah, the future we have is based on data. And today, I think I can proudly say that future is running on Cumulo. Now, open it up to a lot of questions. We say we only have 7 minutes left. I think we all cleared our calendars, and there was a lot of fun ones coming in. So, Dak, can you just ask the hard ones here? Ask the fun ones. Ask the ones that make Aaron cringe.
Absolutely. Yeah.
Don't ask any of Brandon. Okay.
Here's one for Aaron. What happens if you set permissions on one edge? Do the permissions propagate instantly, or is there a delay?
The permissions, like the data, are consistent and correct. So basically, you set the ACLs. The ACLs are based on SIDs if you're attached to if you're attached to your system. And internally, we actually will propagate that around in our cluster. But from your point of view, from the outside, it looks as though it's one system. It's indistinguishable if you're on any end of the portal.
Thanks. Here's another one. I'm just gonna keep Adam here. I'll try and sort them out based on presenter. For you, Aaron, does the client maintain the inner cloud gateway, or is Cumulo pre-provisioning them? In other words, explain portals.
Wait a minute.
Does the client maintain the inner cloud gateway, or is Cumulo pre-provisioning them? I can read that question a couple of different ways.
Yeah. I mean, I guess the basic answer to that is wherever the clusters live, they set up a mesh connection, a mesh of connections between them to be able to transfer data back and forth. It's more than one TCP connection, but however that connection gets set up, it doesn't really matter to us. Like the networking in between is very flexible, and we can work in a lot of different systems.
Thanks. Here's one. I'll just answer it quickly. Can you deploy an edge server in the cloud with Terraform? Absolutely. You can deploy CNQ on the cloud of your choice with Terraform.
Dak, can I use CloudFormation? Can I use Pulumi? Come on, don't be so dry, man.
Yeah.
There are multiple ways here.
There's just so many questions I'm desperate to answer, Doug. Yes, on AWS, if you like CloudFormation, we have the equivalent feature functionality for CloudFormation versus Terraform.
Can I use Ansible too?
You can always, if you're an Ansible shop, put Ansible on top of the Terraform we offer and automate us within your CI/CD pipeline with Ansible or the other tools you choose for your CI/CD pipeline.
And would that be because everything is accessible and available by a full API that's version controlled and RESTful?
Absolutely. Two things go on there that often get conflated. So the Terraform that we provide as an example, or the CloudFormation, that is to deploy the infrastructure. Doug he likes to push my buttons. That is to deploy the infrastructure. You need to use that. We put a lot of work into it. It's really good. Customers love it. It deploys clusters. It'll deploy a 100-node cluster in 6 minutes. But then the real beauty comes, let's say you've got Ansible on top, you call the Terraform, it deploys the infrastructure, and now you want to set up shares, quotas, exports, you name it, within the file system, you can do that all via our REST API. You can do it with CLI calls if you're comfortable with that. You can write directly to REST and download our API and go to town in the language of your choice. It's up to you.
I'm going to make you a DAC in the box where I wind you up and you pop out and give answers.
Just looking through questions here. Here's a great one, Aaron, and I think this would be really good for you to talk about this one. Are there controls to limit the amount of data that's transferred to the cache? In a cloud world where data transfer is charged per gigabyte, is there control to stop mass amounts of data being transferred by accident? Let's go ahead and just focus on the first one first and foremost.
You can, well, right now, the way that we actually do it is the cache uses up the rest of your space on your cluster. But it's, so you can actually have local files on a cluster and cache files for a portal for the Cloud Data Fabric on the same cluster. And what happens is the cached files just use up the rest of the space. When you write more files into the local part of the cluster, it'll evict files out of the cache in the Cloud Data Fabric part of it. So that's like the usual way it goes. We don't currently actually have a limit on there saying you can't, where you can only use so much cache. We don't have that right now. We do have a thing where we could actually, you can put a quota on your normal stuff so that you guarantee a certain amount of cache for your portal.
Right. So we dynamically manage the cache on an existing cluster, right?
Yeah, exactly. And the cache doesn't actually show up as used space because it's evictable on demand. Whenever you need the space for something else, it'll evict stuff out of the cache.
Perfect. Another really good one here is how would the auditing work? Currently, we can send stuff to Splunk, but how can we capture all the events for a file system?
Yeah, the way that we set up auditing is each of the, I'm going to start using the terminology hub and spoke because it's what we use internally, but the hub is the data core, the spoke is the edge cache. So basically, we set up auditing on on the hub and each of the spokes. And you can send all of those to the same Splunk or whatever. And you need to do it that way because since it's cached on the spoke, you could actually have 3,000 accesses for the same file. If you want to audit each of those, you need to do it on the spoke because he's the only one who knows about it. The hub doesn't even know that those accesses are happening because it's cached.
Exactly.
Here's a leading question. If you have this is a softball. If you have a preemptive read-ahead cache that is an aggressive read-ahead cache that runs inside of a cloud instance, and it has some insanely high cache hit rate, which I'll let you guys brag about, does that reduce the number of API calls I'm making against my S3 buckets and so on as well to improve overall cost as well as performance?
Go for it, Aaron.
Wow, that is quite a leading question.
Yeah, before Aaron answers, though, I will just say, this was one of my exact first questions when I first saw the potential of the roadmap coming from AWS. I was like, oh, you're going to run a file system on S3? Like, have fun with those API calls. Just let me know when you get the bill, right? So, Aaron, sorry, over to you.
Yeah, inside of our CNQ, Cloud Native Cumulo architecture, anything that's cached is actually cached on SSD. When you multiple requests will go to the SSD, you will not continue to go to the object store to be able to get the same data multiple times. And so that actually does drastically reduce your transaction costs, as alluded to by Douglas.
Okay.
Yeah.
Hold on, real quick, Aaron. What like cache hit rate are we seeing on that in practical purposes?
Maybe Brandon or Dak should answer that.
Yeah, I was curious because we have the fleet statistics, especially on the SaaS offering that we have in Azure as well. So our global fleet average is a 96% read cache hit rate, which is unfathomable to me. I mean, growing up in the scale out NAS world, your good day is like 25-30% most recently written data. So I don't really understand the dark magic and pixie dust and unicorn tears that Aaron has put into the product, but it's hitting 96%, which basically means two huge benefits. One, I mean, 96% of all your data is basically the feeling of straight NVMe north-south networking without any other getting in the way. In fact, one of the validation teams at AWS told us we had the highest theoretical to realized performance on instances of any file system, third party or native, they've ever tested, because how efficient it is using those resources. And so you get 96% pure NVMe performance, but at the cost of S3 intelligent tiering, S3 GIR, and then on top of it, it avoids a tremendous amount of API charges. So the compaction and compression of the data on the write cache plus that read cache hit rate. A typical customer for an active S3 bucket or Azure Blob bucket will see 15 to 20, maybe 25% of their charges for the month be API costs. And that's on normal S3 workloads. If you talk about a file system, you should expect that I've seen ones go up to over 100% of their, cost to store the data being API costs.
And Brandon, real
average.
quick, just to again lead the witness. And if I'm using a workload like, say, I don't know, PyTorch or a transform that's doing multiple recursive repetitive reads against the exact same file set again and again and again and again, say an AI modeling world, that would be even more pronounced.
Yeah. And so customers in that circumstance, by the way, are faced into kind of one of two situations. Either one, the perceived cheaper way of just directly accessing the object store and getting hit with those APIs over and over again, which is really just getting you on the back end. Or two, use file mode where you then copy it into the local NVMe of the disk before doing it. Both means either you're paying for it on that side or you're paying to run GPUs while they sit idle and load data. Both are bad situations. So in contrast, our API charge on average for our customers is sub 1% for our active systems versus that, 15 to 20 some odd percent, upwards of 100% for certain file systems. And, not only is this beneficial, obviously, for the wallet, but it's beneficial for user experience. It's beneficial for avoiding idle GPUs. All those things really just add on to how it's helping our customers out.
Just awesome. Hey, Aaron, one quick question for you. As the chief architect, can you just reach behind you? What is that, like a Ducati 996 you made? What is that behind you?
Yes.
Yeah, it's a Lego Ducati. It's one of the January Wave sets that came out. I built. I'm kind of a Lego fan, so
What is in those black binders behind you? What are those?
that's about 250,000 Lego parts, like organized meticulously, in my own sort of OCD way. Yeah.
Is it like that movie High Fidelity where John Cusack keeps constantly rearranging his record collection by genre, by year, by
Autobiographical? Yeah.
Now, Aaron, only if you had like a way to be able to instantly curate and know where all those blocks are at all times, no matter what bin they're in. And then, like, I don't know, like a management overlay interface to see all systems in a global data fabric we might call like Nexus or something like that as well. That would be pretty cool.
Well, we
and
can
by the way,
stretch that. We can stretch this analogy. Yeah, like
does everybody understand now, looking at the left side, looking on the right side of Aaron, why there's this cool Ducati? On the left side, the world's most amazing organizational structure of Legos, that we said we want to take the junk drawer of data that is this legacy mode and say, dear Aaron, please be the Marie Kondo of data and organize this for us so it's easy to find. And I know what piece to find. I usually organize my Legos into salad bowls when I'm making things. And you have it like literally by piece, by color, by shape.
indeed, it's what helps me relax.
Awesome, man. All right, Dak, we probably
Well,
time for one more question. What's the
the
closing?
questions just keep coming in. And we're pushing 10 minutes over here. We want to respect everyone's time. We got a lot of people on this webinar. And we also want everyone to be able to hear and see the answers for those that did have to drop at the top of the hour. So what we're going to do is we will answer any questions that we weren't able to answer live after the fact and get back to those attendees. And with that, I just want to thank everyone that was able to hang a couple more minutes with us. Thank you, Doug, Brandon, Aaron, and all of our attendees. We look forward to working with you, collaborating and enabling your data and help you monetize it with Cloud Data Fabric. Thank you.
Awesome, everybody. Thank you so much.
Thank you.
Thank you.